My name is Haley, and today I will be talking to you about silver catalysis. But first, it is important to understand what a catalyst is. A catalyst is something that aids a chemical process that is taking place. Catalysis is important, however, it is not well understood and isn't a very appreciated branch of science. It is used to alter the path normally taken, and as you can see on the right, you can see that a reaction that occurs without a catalyst takes a lot longer to form the product than with a catalyst, as it makes the reaction go faster, and sometimes without the use of a catalyst, a reaction will not occur at all. Catalysts aid in transforming one chemical into another without even altering the catalyst. It allows for efficient production of almost all industrial chemicals. Many aspects of green chemistry would not be possible without the use of a catalyst. So considering all of that information, what is silver catalysis? To understand silver catalysis, it is important to understand silver. Silver is a malleable, ductile, and precious metal that has been known since ancient times, around 5000 BCE. Silver is widely distributed in nature and is in an abundance in the Earth's crust. It can occur naturally in its purest form, or it can be found in ores. In particular, it can be derived from all the sulfur-bearing lead, such as copper, gold, zinc, and more, which is extracted through the refining process. Silver is used as a homogeneous catalyst and is used due to its high oxidation power. It also enhances the electronegativity of other catalysts, such as gold. Silver is the best electrical and thermal conductor of all the transition metals, making it such an amazing catalyst as it is relatively lower in cost compared to the other expensive transition metals, and it also has excellent selectivity and stability. It is mostly used in industrial fabrication to form conductors, switches, contacts, and fuses. The rapid development of silver chemistry was achieved only in the past couple of decades. Silver salts are also employed as co-catalysts, halophiles, general oxidants, and radical initiators in numerous transformations. The picture on the left is a factory supply of silver catalysis that would be used in a reaction. It is called silver carbonate. So, considering silver catalysis, how are catalysts used in organic chemistry? Well, silver catalysts are widely used in organic reactions as Lewis acids. In earlier years, the utilization of silver could be classified in two main areas: heterogeneous oxidation process and homogeneous silver-mediated processes, or other known as silver catalyzed reactions, which I will be focusing on today. Now, there are many ways to apply silver catalyzed reactions, such as cycloadditions, redox reactions, arylations of carbonyl and imine groups, carboxylations, aldol reactions, and Michael and Mannich reactions. We will see some examples of different reactions in the following slides. First, we must consider how silver catalysis is used in the industry. The first silver catalyzed reaction occurred in 1933, and that was with ethylene oxide, in which ethylene was oxidized into ethylene oxide through the use of a silver catalyst. Since then, many silver catalyzed reactions have been developed and even applied in the synthesis of complex natural products and many other functional materials. Because of silver's unique chemical properties, silver is a vital catalyst in the production of two main industrial chemicals, like I said earlier, ethylene oxide as well as formaldehyde. Silver is used in these reactions as it allows for faster production of ethylene oxide and formaldehyde. As well, it does not get consumed in the reaction, and therefore it is almost completely recovered after its use, and is also able to be reused for many other reactions, which makes silver catalysis so valuable. It is important to understand how silver is used in formation of ethylene oxide. Without the use of silver as a catalyst, the production of ethylene oxide to the degree that it is produced would not be possible. The world relies heavily on the production of this chemical. Nearly 10 million ounces of silver are used each year to produce ethylene oxide. It is fully reliant on the silver catalysis in order to produce the reaction, and the final product. Ethylene oxide is the foundation for plastics, including polyester. Polyester is a textile that is used in both mainstream fashion and specialty clothing. It is also used for insulating handles for stoves, keytops for computers, electrical connectors, and many more. About 25% of ethylene oxide production is used to manufacture antifreeze coolant for vehicles. The reaction that ethylene oxide goes through is an alkene epoxidation, which is a critical process in the chemical industry. It is also important to note how silver aids in the formation of formaldehyde. It is a chemical produced from methanol to be able to form formaldehyde, which you can see on the left in the reaction scheme. The reaction to form formaldehyde goes through the silver-catalyzed oxidation of methanol and remains the primary industrial process for the formation of the formaldehyde production. It is the building block of solid plastic adhesives, laminating resins for construction plywood, and particle board. It is also useful for finishes on paper, textiles, and electronic equipment, and occurs through the anaerobic dehydrogenation reaction. And compared to other catalysts, the silver will operate at a higher temperature than most catalysts, usually around 650 degrees Celsius. This is the first successful example of a heterogeneous catalyst. A heterogeneous catalysis is catalysis where the phase of catalysts differs from that of the reactants or products. This means that the reactants, products, and catalyst all will exist in the same phase. For example, liquid, solid, or gas, and even immiscible liquid mixtures like oil and water. It typically involves solid phase catalysis and gas phase reactants. This catalytic technology actually dates back to the 1880s and was first used with non-plutonium-based catalytic industrial processes. So, let's talk about some different types of reactions. Today I'll start talking about isocyanide alkyne cycloadditions. The cycloaddition of isocyanides and alkynes is a straightforward method for the synthesis of pyrroles, which are important motifs in many natural products, such as pharmaceuticals and agrochemicals. A silver-catalyzed cycloaddition reaction of inactivated terminal alkynes and isocyanides is usually used with silver carbonate, as it has exhibited unique catalytic activity towards the pyrrole synthesis, much more so than other silver salts such as silver nitrate, silver tetrafluoroborate, silver perchlorate, and silver acetate, and many more. This reaction is best with this catalyst as it does not produce any byproducts from the coupling that occurs with the terminal alkynes. The mechanism on the left is a reaction that undergoes a multi-catalyzed radical process where the silver carbonate serves a dual role as the base for deprotonating the isocyanide and an oxidant to initiate the initial isocyanide radical formation. After the cycloaddition of isocyanide radical with silver acetylide, the substrate and solvent replace the role of the silver carbonate and acts as a radical shuttle to regenerate the isocyanide radical for the next occurring cycle, which then completes the protonation. Another good example is the redox chemistry of silver. Silver 1 salts are extensively used as one-electron oxidants compared to that of the other group metals, like copper and gold, that are involved in 2-electron redox chemistry. Today, I'm going to be specifically talking about one-electron chemistry between silver 1 and silver 2 redox cycles. Silver 1 is involved as an efficient catalyst in the oxidative decarboxylation of acids by peroxide disulfate ion in aqueous solutions. The intermediate silver 2 species from the rate-limiting oxidation of silver 1 by the peroxide disulfate aids in the direct oxidation of the carboxylic acid group by silver 2, which proceeds very fast and generates an acyloxy radical, which fragments into the alkyl radical. The reaction on the left mechanistically forms the metastable intermediate of the silver 2 species, from the rate-limiting oxidation of silver 1 by peroxydisulfate, which plays a crucial role in the specific and efficient decarboxylation process. The direct and facile oxidation of the carboxylic acid group by silver 2 proceeds very fast and generates that acyloxy radical, which subsequently fragments into an alkyl radical and carbon dioxide. The final products are obtained by oxidation of the alkyl radical by silver species as well as by the hydrogen transfer to solvent. Another example is the hydroazidation of alkynes. This reaction is one of the most straightforward pathways to synthetically form useful vinyl azides. Compared to other catalysts such as copper-1 and palladium-2, most salts fail to yield the hydroazidation product. The silver is useful as it can establish the chemo- and regioselective hydroazidation of ethynyl carbonyls in high yield. Mechanistically, on the left, silver acetylide and vinyl silver were proposed as a key intermediate in this reaction. Later, though, it was found that the stoichiometric amount of water was able to be avoided through the dependence of the hydroxyl group in the hydroazidation reaction. Accordingly, the numerous unactivated terminal alkynes underwent the hydroazidation using trimethyl azide in water with the assistance of silver carbonate to give the excellent yields of the corresponding vinyl azides in even shorter reaction times. Another great example is nitrogenation of terminal alkynes. It is the transformation of alkynes as a fundamental method that has been used widely in organic synthesis. The catalytic selective cleavage of the carbon-carbon triple bond has attracted significant attention as it forms new carbon-carbon bonds, especially in the presence of the silver catalyst. The mechanism on the right shows the formation of vinyl azide as the crucial intermediate in this nitrogenation reaction, which could directly transform into corresponding nitriles under standard conditions. But in the absence of another equivalent of trimethyl azide, corresponding nitriles obtained in very poor yields imply the pivotal role of the trimethyl azide in the carbon triple bond cleavage. From this concluded that the conversion of vinyl azides into nitriles does not require the silver catalysis. Then, as it reformed, vinyl azide cyclizes with azide to form the unstable intermediate, which undergoes fast rearrangement to give the nitrile with the release of hydrozoic acid and diazomethane, which then proved that the silver catalyst would be needed in order to keep the product formed, instead of it reverting back. The silver carbonate as the catalyst is used to obtain the desired nitriles in high yields. Another example is enantioselective nitroso-aldol reaction. This reaction is one of the most important transformations in organic synthesis that is able to introduce a hydroxyl group at the alpha position of a carbonyl compound. The goal of this reaction is to control the selectivity of the oxygen and nitrogen towards the high reactivity of nitroso derivatives towards nucleophiles. Generally, an organocatalyst like L-proline will exclusively promote oxygen-nitroso-aldol reactions of aldehydes and ketones. But the selective nitrogen-nitroso-aldol reactions are very difficult to achieve. However, with the use of a silver as a catalyst, it has made it a lot easier. It can selectively achieve the N-adduct in the nitroso-aldol reaction of tributyl enolate with nitrosobenzene using 10% mole of AgOTF and the R enantiomer of the BINAP system. When this study was conducted on N-nitrosos aldol reactions, they isolated 3 different BINAP silver complexes via the systematic survey of metal to ligand ratio. Each of the 3 complexes were found to play different roles in regio and enantioselectivity of this nitroso-aldol reaction. The best complex used was the R enantiomer of tolbinap and the AgOTF and trimethylatin enolate and nitrobenzene. The silver reagents play different roles in regio and enantioselectivity of the nitroso-aldol reaction, making them vital catalysts to produce the final product. Another example is the fluorination reactions. This reaction is the replacement of a hydrogen by a fluorine in organic molecules, which leads to dramatic changes in the molecule's solubility, bioavailability, and metabolic stability. This reaction is with silver catalyzed and silver mediated approaches to occupy a prime position for the synthesis of fluorine-containing molecules. The first reaction on the top right, I will be talking about introducing a fluorine atom into the sp3 carbon via silver catalyzed decarboxylate of fluorination of aliphatic carboxylic acids using select fluor as the fluorine source. This reaction occurred during aqueous conditions. The reaction used 20% mole of silver nitrate as a catalyst and various aliphatic carboxylic acids to undergo the decarboxylate of fluorination to produce the fluoroalkanes in high yields and good chemoselectivity. The reactivity of said carboxylic acids decreased in order from tertiary, secondary to primary, and then to aromatics. The mechanism is a radical mechanism to show the formation of silver 3 fluoride intermediate via the oxidation of silver 1 by select fluor as the most critical step. This undergoes single electron transfer with the carboxylate ion to produce silver 2 fluoride and the carboxyl radical. The fast decarboxylation provides the alkyl radical, which then abstracts the fluorine atom from the silver fluorine to make the alkyl fluoride and then regenerate the silver catalyst. This is a great example in order to demonstrate how crucial silver is as a catalyst in organic reactions. The second reaction I will be talking about is silver catalyzed intramolecular aminofluorination of allenes for the synthesis of 4-fluoro-2,5-dihydropyrols. Silver nitrate is a remarkable catalyst as it has remarkable catalytic reactivity while using N-fluorobenzene sulfonamide as the fluorine source. This reaction is tolerant to various functional groups and substitution patterns. Silver is used as the catalyst as most other catalysts such as palladium are not able to convert the product, thus indicating how crucial silver 1 is to the reaction for the desired outcome. The two types I focused on specifically are called decarboxylate of fluorination and aminofluorination. So now that we've talked about some reactions, I just thought I would end off this PowerPoint by discussing a very interesting application of silver. So silver and silver nanoparticles have been used as an effective antibacterial agent against broad spectrum of gram-negative, such as Escherichia and Salmonella, and gram-positive, such as Listeria and Streptococcus bacteria. This means that silver is very toxic to bacteria and is used in a lot of medical and health industries to aid in fighting diseases and spread of bacteria globally. They are also found to have antifungal, antiviral, antibiofilm, and anti-inflammatory and more biological properties. So, thank you for listening, and this is my dog Callie. Thank you, and is there any questions?